a great pleasure for me to introduce our speaker today. She's Catherine Fries, a professor of physics at the University of Michigan, and also she is guest professor at the Oscar Klein Institute in Stockholm, where she served as well as director of Nordita from 2014 to 2016. She is an expert in theoretical cosmology and astroparticle physics, and she is recognized as a leading expert in the study of dark matter. Along her career, she has received many honors and distinctions, as for instance, an honorary doctorate from the University of Stockholm and the Simons Foundation Fellowship in Theoretical Physics. Very recently, she has been awarded the Lilienfeld Prize from the American Physical Society for, according to the committee, for the groundbreaking research at the interface of cosmology and particle physics, and her tireless efforts to communicate the excitement of physics to the general public. Indeed, in this sense, we can highlight the publication of a book for the general public with the title The Cosmic Cocktail, 3 Parts of Dark Matter. Although this is her first visit to Valencia, she has a close connection with our institute since she collaborates with our colleague Olga Mena, and in the future she will be the supervisor of our colleague Pablo Fernandez, who is defending his PhD thesis next week. Okay, before closing this short introduction, I would like all the organizers of the colloquium would like to thank the Ramon Arances Foundation, represented today by Professor Manuel Aguilar, for the support to the series of conferences, si ellas pudieron, tú también, and of course the organizer of these conferences, our colleague Gabriela Barenboim, that have supported the visit of Professor Fries here today. So I leave it with the speaker, so she will tell us about the dark matter in the universe.
I'm turning on the microphone. I see that it works?
Yeah.
Okay, very good. So I wanted to, first of all, begin by thanking you so much for this invitation. So thank you from the university, and thank you from the foundation. And I'm having a lovely visit. So this is, and it's wonderful to finally meet my collaborator of at least 5 papers, and that would be Olga Mena. So it's nice to be here, and so thank you, Manuel, thank you, Gabriela, thank you, Miriam, and thank everyone for inviting me. So I wanted to begin by some comments in general about cosmology, about the origins of our field, which started 100 years ago with the theoretical work of Albert Einstein in relativity. And soon after he proposed relativity, well, it was tested and shown to be right, but then it was also applied very quickly to the universe as a whole, under the assumptions of the symmetries of homogeneity and isotropy for the universe, namely that it's the same at all points and the same in all directions on the average. So if that's true, then there are 3 possible evolutions for the universe. It could be static, expanding, or contracting, and Einstein had a favorite. He wanted an additional symmetry, the symmetry of time. He wanted a static universe. And he actually added at that time a very finely tuned cosmological constant to make that work. But of course we know now, since it wasn't much longer, it was in 1929, the work of Edwin Hubble in the Mount Wilson Observatory above Pasadena, that he first of all proved that galaxies beside our own existed, which had not been known before that time. And then he studied them. In fact, he studied atomic emissions from elements inside the distant galaxies. The atomic emissions have a known wavelength, and then you observe them today and see what happened to that wavelength. And what he found is that it was stretched, much as if you were to blow up a balloon, the wavelength would stretch. The conclusion from this was immediately clear that the universe must be expanding. So our general model of the Big Bang, well, it's more than a model. It's really amazing, the predictions that turned out to be true. So we really do have an understanding of the origins of the universe in some fundamental way, although the model's incomplete. So we know the universe is roughly 14 billion years old, and it started in a soup of tightly packed quarks and leptons, photons, other particles, very hot, interacting, tightly packed. And then as the universe continued, it expanded, and in the process cooled off, with things moving apart from one another. So eventually the quarks able to form neutrons and protons, and later heavy elements and so on, and eventually making the galaxies that we live in. A simple-minded picture of the universe expanding would be something like this, where you have, this is a piece of raisin bread with raisins, but it's a model for the universe with galaxies. So as the raisin bread expands, the individual pieces move apart from one another simply because they're sitting inside an expanding space, which is a model for what happens with the galaxies in the universe. The difference is that, that the raisin bread has a center where we believe the universe does not. So whichever galaxy you went to, you would really see on the average the same thing. Other than the local galaxies that you might be merging with, on the average galaxies moving apart from you, no matter where you put yourself in the universe. So if we go backwards in time, I always like to emphasize this, take an infinite universe and contract it backwards, it's still infinite. So the Big Bang is not a point in space, it's a point in time. It's the point in time where things were so dense that our laws of physics fail and we need quantum gravity to go any further back. So over the last century we've had tremendous progress, and in particular, right around the turn of the millennium, amazing discoveries. The geometry of the universe, the energy density of the universe, the age of the universe. But then I will turn to some of the remaining questions. What is the universe made of? I do have a few slides about how the geometry and total content of the universe were discovered. So I wanted to talk about this cosmic microwave background, the leftover light from the hot early universe, from when very early on everything was colliding with everything else, including photons. They couldn't go very far. But once the universe reached about 400,000 years in age, then the electrons that the photons were quantum scattering off of, those electrons disappeared into hydrogen atoms, and then the photons proceed. They don't scatter anymore. We call this the surface of last scattering. And since that time, the photons come to us, and we see them today as microwaves. So how can we use this to learn about the geometry of the universe? Well, what we want to know is, in the three possible geometries, is light moving in a straight line, or is it curved because of the curvature of the universe? And you can answer this question. This is the last scattering surface, the last time the photons scattered, and from our point of view, if we're here, that's a sphere that's very far away from us. And the photons move towards us, and the question is, do they move in a straight line, or do they move with curvature? If they move in a straight line, there's a ruler that's imprinted here that tells us that this angle should be 1 degree. So in fact, this was led to a Nobel Prize in 2006 to Mather and Smoot. The way this works is that they measured the microwave. Well, this is not from their data. This is, I'm sorry, this is much more recent. This is the Planck satellite data from the European Space Agency, where you see the microwave background sky, where you have hot spots in orange and cold spots in blue. And the size of those spots tells you the geometry of the universe. And the question is, are they 1 degree, in which case the universe has a flat geometry, or are they something else where there would need to be a curvature? And the answer is definitely 1 degree. And it's now known to better than 0.1%. So indeed, the geometry of the universe is flat. No curvature required. It's a three-dimensional universe, obviously, but the parallel lines never meet. Triangles, angles add up to 180 degrees, even on the very largest scales. Now, Einstein tells us that the geometry of the universe is connected to the mass and energy content in total, and so making that connection in general relativity, that tells us what the energy density of the universe on the average is. It's very small, 10 to the minus 29 gram per cubic centimeter. Let me contrast that with Earth, where we have water at 1 gram per cubic centimeter. So if you go out into the average universe, this is the number that you would find, and I tried to explain this to the Queen of Sweden with an abject failure, but anyway, ask me the story, it's funny. It was embarrassing. But anyway, so from the Planck satellite, we not only know from the location of this first peak what the geometry and the mass energy content of the universe as a whole is, we know a whole lot more from those other bumps. And in particular, these are the main 6 parameters, and one of them, if I had my glasses, I would point to the right one, is the amount of matter that's made of ordinary baryons, and then as opposed to the amount of dark matter, the amount of dark energy. These are some of the basic parameters that you get from fitting those 7 peaks in the microwave background. All right, before turning to the today's big questions, I wanted to mention the previous satellite, the NASA's Wilkinson Microwave Anisotropy Probe. So it's the same data, just different color, shown in different colors. And here we go. It's easier to see in these colors. Stephen Hawking. So what big questions do we have today to answer in astroparticle physics? Okay, what happened very, very early on? What is the right inflationary cosmology? And there's a lot of progress being made, in particular, again, using the cosmic microwave background on the side of data and on the side of theory. We have people like Gabriela, who's making progress in understanding what happened very early on and possibly relating it to today's acceleration as well. What I want to focus on, though, is the other question: what is the universe made of? What is the dark matter? What is the dark energy? And I'd like to mention, if I can, at the end, something about dark stars. So everybody in this room knows this, but the universe is a very strange place. If you take everything we know about you, your chair, the air you're breathing, the entire Earth, the entire solar system, everything that we're familiar with in our daily existence, all made of atoms, made of quarks, only adding up to 5% of the universe. And, oh yes, I threw in a cocktail too, but anyway, so all of that is only 5% of the universe, where dark matter is 25% and dark energy is 70%. I thought I would mention the strange discrepancy between the US, the NASA satellite, and the European satellite, that the numbers are slightly different. In fact, Planck gives us slightly more dark matter than more recent data. So this difference has to be ironed out at some point. So there's obviously only one right answer, and they're looking at the same data set. Planck with much greater resolution. Now the question of the first evidence that dark matter could exist dates back to the 1930s. And I wanted to mention Fritz Zwicky, the Swiss scientist working in Caltech, also using the same telescopes as Hubble, who looked at the Coma cluster of galaxies, a very rich cluster, lots of galaxies, and some of them were moving very, very rapidly. Based on the stellar light that he could see, they shouldn't have been moving that rapidly. So he postulated, well, there's a gravitational attraction from something else. This would be the dunkle materia, or the dark matter. Dark meaning it's not stars, it doesn't shine. That's the only meaning behind the word dark. And some of you may have heard stories about this guy. So he called in his book, he called his colleagues spherical bastards, because no matter what direction you look at them from, they're still bastards. So, yeah, we hear about some tough PhD advisors, but I don't want to be this guy. But, well, anyway. So after that, there was a lot of, can I tell one more funny story, or should I? Yeah, okay. So I did this bizarre radio interview at 2 o'clock in the morning till 5 o'clock in the morning. It's called Coast to Coast Radio, and it's truckers who listen to this, and they're very interested in UFOs. But so somebody called, they call in with questions, and so this woman called in, Barbarella. And I said, hi, Barbarella. And she was Barbarella Zwicky, the daughter of this guy. And to this day, she's bitter that nobody listened to him about dark matter. Bitter, bitter, bitter. And I didn't know it. I just said, well, we're listening now. So evidently, it took some time for this problem to be generally accepted as beyond the discovery of just one cluster. And it was really in the 70s, the work of Vera Rubin and Ken Ford that completely convinced the entire community. So they studied rotation curves of many, many galaxies and found that they were flat, so I wanted to tell you a little bit more about that. So here we have a galaxy, and as you move some distance from the center, you can observe the motions of things, of gas or stars or whatever, moving around in the galaxy, and then you can ask, how fast do they move? And if we apply the virial theorem, then the speed is determined by the mass interior to that radius. So how much mass is in here determines how fast it moves. And they found results that were not, well, that basically require dark matter. So here you have, as a function of the radius from the center of the galaxy, here's the speeds of things moving around. And if you only had the stellar light, this is what you would expect. But that's not what they saw. They saw instead these flat curves. By the way, this is somebody else's work that I'm plotting here. He wrote to me very angry that he wasn't appropriately referenced in some other talk that I gave. So I want to make very sure you know, this was not from Ford and Rubin. Anyway, oh my God, I'm being taped. I shouldn't have said that. Can you delete that sentence, please? But anyway, of course, you want to attribute properly. And so this is the man who did this particular galaxy. So you see this flat rotation curve requiring, well, if you add in the dark matter with this additional material, then you can explain this flat rotation curve. So what does our galaxy look like? At the center of the Milky Way, shown in yellow, is a supermassive black hole weighing 4 million times the mass of the sun. And then you have this, like a pinwheel, these spiral arms of structure, and there you go along one and you hit the sun. Now take this entire thing and look at it from the side. And here we are, 25,000 light years away, or 8 kiloparsecs away from the central black hole. And if you take now this entire disk, where all the stars are located, and you look at it in the bigger picture, this is of course an artist's rendition, then you would have something like this, where the disk is this flat plane surrounded by a giant spherical halo of dark matter. I don't know the origin of the word halo, but okay. So rotation curves insist that something strange is going on, and then since then we have many pieces of the puzzle that show you dark matter has to be there. In fact, I mentioned briefly, but really the thing that really nails it is actually the cosmic microwave background. You can't live without dark matter in terms of explaining those peaks. But I wanted to mention also some others, which is this one, Einstein's gravitational lensing. So as we know from relativity, mass bends light. And so if you have any type of dark matter, for example, a massive compact halo object, it will bend light. So it doesn't give off light, but you can identify you can find it by looking how it acts on the light behind it. So the light from the star moves in a curved path, no kink, that's just my bad picture. So it moves in a path to the telescope so that you would see something over here in the wrong location, but and you would know because, first of all, it's extremely distorted, and second of all, you could see multiple images of the same thing. So gravitational lensing is a very powerful tool for locating, for identifying the distribution of dark matter in the universe. And, oh yes, there's an app on your phone, go get it, created by a Michigan graduate student. You can lens yourself. In fact, you can lens yourself more and more, weak lensing, strong lensing, whatever you like. So this is data from Hubble Space Telescope, and there are many there are galaxies in here, there's mass in here lensing background galaxies, and there's a lot of lensing going on, and don't ask me the details, but from that you can reconstruct the dark matter in the path between the bright objects and you, and then by doing that you get something like this. This is not the same object as the previous slide, but it's the prettiest one. So what we have here is again a cluster. I think it's the same one that Vicky was looking at, and this is the mass distribution. Okay, so you see the galaxies. You also see additional mass from this reconstruction of what had to explain all those sheared multiple images before, and you can see there's dark matter in between the galaxies as well. So another piece of evidence that there has to be something other than ordinary matter is shown by the bullet cluster, where you have two galaxies that have collided. Eventually they'll merge, but by chance they were observed right after the first collision, which is great because you can see the differentiation between two types of different behaviors of different types of mass. So in pink is shown the gas, which is giving off X-rays. That's how you know it's gas. And so what happened is that the gas collided in the collision of the two clusters. The gas got stuck. Didn't get very far. It has electromagnetic interactions, strong interactions. It got stuck. However, from lensing you can also see this blue material, and that's something else. So it's dark matter that did not have electromagnetic or strong interactions, and so it continued moving. Eventually gravity will win and the whole thing will come back together and make one single object, but that hasn't happened yet. So I've shown rotation curves, and then this to larger distances, gravitational lensing, the bullet cluster, and the peaks in the microwave background, indicating the existence of dark matter. Now, one more important role that dark matter plays is that it allows galaxies to form in time for us to exist. So if you only had ordinary matter, then it would not be able to clump. The reason for that is in the ionized early universe, the ions were coupled to the photons by Compton scattering, and so photons streaming out of things would pull the ordinary matter with them, and you'd never be able to form a structure quickly enough. Dark matter doesn't have electromagnetic interactions, it's immune to what the photons are doing, and it starts clumping sooner. So in the next few slides, the simulations from Andrei Kravtsov, I've taken here initial conditions from inflation where you have some pockets of the universe that have more mass than others. These perturbations set in very early times. And then the dark matter particles shown in blue. And so they're not entirely uniformly spread out. There are slight perturbations, fluctuations. And the regions with more dark matter will clump more and more and more and form galaxies and clusters and so on. So let's see that happen. So starting in the early universe, and observe the dark matter clumping until you get to, this is meant to represent today's universe in these simulations, where you have filaments of structure and dark matter, and galaxies and clusters at the nodes of the intersections of these filaments. Okay, so we have this pie chart of the universe where you have 5% of everything in our ordinary lives, 25% dark matter, and the rest dark energy, and we'd like to know what is this stuff. So I'm going to focus on the dark matter problem, and right away you might say, what about rocks or dust or something ordinary? And that was ruled out quite early because of various observational consequences if you had a lot of these possibilities. So 20 years ago, there were still two camps. There were the believers in the massive compact halo objects, or machos, and the believers in exotica. So you have to remember there was a time when we didn't know the total mass density of the universe, so it was still possible that atoms were enough. Okay, and so in this category you would have not ordinary stars, but very faint stars, or substellar objects, and so there was a debate between these different candidates, and I actually worked on both sides of the debate. And on the side of the machos, as I said, faint stars or stellar remnants, then we showed that these can only be, the very faint objects can only be about 3% of the galaxy, and then the stellar remnants, it's still possible it might have 15% white dwarfs. But in the end, baryonic dark matter is not enough. Machos are dead, desperately looking for WIMPs. Okay, so returning to the question of possibilities for dark matter, people on the whole think it's some kind of new fundamental object, maybe some new fundamental particle. The easiest would have been neutrinos, but even already in the 1980s, it was pretty clear they would be problematic because they're also known to be light. They were known even then to be light. They would stream out and ruin structure formation. And the contribution of neutrinos to the universe is given by this number. This is the fraction of the total in terms of neutrinos. So if the sum of neutrinos weighed about 100 eV, then they would be the entire content of the universe. So if you, but the reality is, and we've known that since, well, there was a Nobel Prize a few years ago, that the sum of the neutrino masses adds to roughly 0.1 EV, which means they contribute 0.5% of the mass of the universe. They are not the dark matter. They are simply too light. But in this search for what neutrino mass is, I did want to say some comments about this, since I've been working on this also with Olga Mena, who's here, that we know from solar neutrinos and atmospheric neutrinos the mass differences between numbers 1 and 2 and between those and number 3, where those numbers refer to mostly electron neutrino, mostly muon neutrino, mostly tau. But we don't know if 1 and 2 are the lightest, with 3 the heaviest, or if it's the other way around. This is the normal hierarchy or the inverted hierarchy. So we don't know exactly what the mass is. Oscillations put a lower limit on the mass scale in both cases of these kinds of numbers. And the amazing thing is that what we really want to know is not just the mass differences, but the actual scale of neutrino mass. And there are many ways people are looking for this with neutrinoless double beta decay or tritium beta decay. I wanted to mention our work on using cosmological observations, cosmic microwave background, and very importantly, large-scale structure. So for example, if this is the amount of power on different length scales and in forming galaxies and so on, and you can see as the neutrino mass gets larger, it suppresses small-scale structure. And so you can go measure, you can go look at large-scale structure, how much is there, and believe it or not, we have some very good bounds by doing that, and so our bounds are something like the sum of neutrino mass is less than 0.1 eV at 95% confidence level. So if this is Hubble constant versus neutrino mass, then Planck puts you in this large window here, but we used also data from large-scale structure to make this window much, much smaller. The combination of the two is very, very good. So our papers are now regularly in the particle data group's review of particle properties, these numbers. For those of you who are getting perhaps too detailed now, but for those of you who are interested, it turns out neutrino mass bounds are actually tighter when you leave the standard lambda CDM cosmology and instead you go to a different equation of state. As long as it's bigger than -1, the bounds are actually tighter. Okay, so let me return to, one more comment on the microwave background, which is very useful for learning about neutrino mass. My group has joined SPIDER at the South Pole and the Simons Observatory in Chile. Well, let's get back now. The neutrinos are not the answer, but what about the other candidates? Primordial black holes are interesting. I don't know, in here, I put them in here. I think there's a lot of attention there, especially since LIGO discovered black holes. But I'm going to talk mostly about the top two candidates for dark matter. Most people would agree, because these were particles not invented just to solve the dark matter problem. In fact, they're byproducts of other theories that solve other problems in theoretical particle physics. So the axion is a particle that was a byproduct of a solution to the strong CP problem in the theory of quantum chromodynamics. You automatically get very light particles, and yet they're coherent oscillations. They're non-relativistic. But amazing, again, cosmology places these tremendous bounds. So on the one hand, you would have too much dark matter if the mass is listed here on this axis. And if you have too much dark matter, if you're on one end, or on the other hand, you would destroy stars. You would pull too much energy out of red giants and supernovae because the axions would just stream out. So there's a window left here if you want to use axions from QCD to explain the dark matter. And these are light masses. So they're shown, these theoretical interesting region is shown in yellow. And the experiments are shown in all these other colors. Some are existing, and then the green ones are coming. And they're going to really start pushing, in particular these microwave cavities here, pushing into this very interesting theoretical range in the next few years. Well, then I wanted to turn for the bulk of my talk to the subject that I've worked on the most, which is weakly interacting massive particles. So these are WIMPs. So there would be billions going through your body every second, but they're not doing much. You have one hitting one of your nuclei maybe once a month. But because they're missing strong forces and electromagnetic forces, they don't do anything to you. But the postulate here is of the four fundamental forces, the one that is possible is that it might have weak interactions, such as is responsible for some types of radioactivity. And they would weigh maybe 1 to 10,000 times as much as the proton. So if you make the postulate that you have in the early universe particles that have weak interactions, and in particular they annihilate among themselves with weak interactions, you can compute with standard thermodynamics how many there were of every type of particle, including WIMPs. And then as the universe expanded, the annihilation had to stop because the particles didn't find one another anymore. And you ask how many are left today, and here's your answer. So basically, if the annihilation cross-section is given by a weak interaction cross-section, then the fraction of the universe comes out to be right to give you the dark matter. So again, omega is the fraction of the universe in this component. So as long as you have a WIMP mass GeV to 10 TeV, a weakly interacting scale for the mass and the interactions, then you get a good dark matter abundance. Another reason that people like WIMPs is because they are definitely there in supersymmetry. So in trying to explain why some theoretical problems, for example, the hierarchy problem, if you have the ordinary diagrams, Feynman diagrams, but then you have also a minus sign and you put a new supersymmetric partner, and then things cancel out and you are able to repress the raising of most particle masses up to the Planck scale. And so if you do that, then for all the ordinary particles in the standard model, we have new partners, the supersymmetric partners. And of all of these, it's the lightest one that would be long-lived and could be the dark matter particle. Another place that WIMPs exist in particle theory is in series of universal extra dimensions, where you have, again, a symmetry which leads to the lightest particle of the lightest Kaluza-Klein particle also could be a WIMP candidate. All right, so now we have these candidates and we have to figure out how to find them. So there is a three-pronged approach. Same Feynman diagram, you don't really want to draw it from 3 times in different directions, but what the heck. So I'm going to talk about these 3 different approaches, and the first one I'll talk about is production of dark matter, where a proton collision could create dark matter particles, which is going on at, well, I don't know if it's going on. We're looking for it, or we're hoping it happens at the LHC and at CERN. And so here in this 17-mile ring, you have 2 proton beams traveling in opposite directions, colliding at intersection points where you have the detectors, and in particular, here we are, this is underground, 100 meters underground, you have the CMS and ATLAS general purpose detectors looking for signs of supersymmetry. A few photos, Fabiola Gianotti, the director, she was the leader of an ATLAS group that was looking for the Higgs, and she's now the director general of CERN. Here's the ATLAS detector, somebody's standing there, just to put it in perspective, and Peter Higgs in front of the other one, the CMS detector. And the LHC did, in 2012, have its first major discovery and found Higgs at 125 GeV. And, okay, obviously the LHC is looking for anything beyond standard model, any type of beyond standard model physics. In particular, a lot of the searches are focused on looking for supersymmetry, where you would have proton collisions giving you supersymmetric particles decaying in a chain to the lightest one, which could be the dark matter, escaping detection and looking like a missing energy. So you have jets plus missing energy as a signature that something is going on, and then you could hopefully discover supersymmetry, but that has not happened. So this is an old plot, but the same idea is still true. So in supersymmetry, if you have a version of that constrained supersymmetry or supergravity, then at very high scales, all the fermions would have the same mass, and all the bosons would have the same mass. And then you would, you would run that down to lower energies to get the particles that we have today. But if you make that assumption, then it's easy to plot it because there's only 5 free parameters instead of the 105 that minimal supersymmetry actually possesses. So if you make that simplification, then here are the data from ATLAS. You have to be above these curves, so you're being pushed up to TeV scales for supersymmetry. I wanted to make a few comments, and the first one is, it is possible the LHC will not find supersymmetry, but that doesn't rule it out, and we knew that before they started. You'd have to go to a higher energy. But if nothing's discovered in the LHC, who's going to pay for this is another question. In addition, it could be that the simplification that I talked about of having only the 5 parameters may just be an oversimplification, and in fact, there you might have non-universal Higgs models or many other types of things, in which case these simple-minded bounds don't apply and you have to re-evaluate everything. But in any case, even if you do find supersymmetry, you still haven't proven it's a dark matter particle because something that leaves the detector may or may not be old enough to last the entire age of the universe. So we have to do complementary searches, no matter what. One approach to this is called direct detection. So these are underground laboratory experiments searching for WIMPs that scatter off of a nucleus. It's elastic scattering, depositing a small amount of energy, keVs of energy, very small energies, and very low count rates, 1 count per kilogram per day. Oh boy, very, very difficult experiments. And I got into this business really through my PhD advisor, David Schramm, but more specifically into these searches with André Druckier I was at a winter school in Jerusalem, and he was talking then in, well, yes, in many languages at the same time. But, so he told me about his work with Leo Studolsky on ideas for neutrino detection, which is also a weakly interacting, weak interaction. And in fact, that has recently been discovered had finally been seen by Juan Collier in an experiment at Fermilab. So they did finally see the coherent neutrino scattering directly. So we arranged for him to come visit Harvard CFA, where I was a postdoc. And then it was, so that's Andre and Leo. And then Goodman and Witten uses notice, well, if you can do it with neutrinos, you can do it with WIMPs. And so we wrote then the second paper on the subject, also with David Spergel. And some of the things that we did, let's look at the event rate. So it's, as usual, any cross-section times number density times velocity is basically the event rate for any interaction. And then you can rewrite this in terms of the particle physics part outside here of this integral. So that's this particle physics part and the astrophysics part here. So as far as the particle physics, the cross-section, we don't know exactly what it is. It could, there are many possibilities, many operators, 16 different operators from the point of view of particle physics. And so, but the two that people generally talk about as far as these searches right away, the first thing you think about is spin independent with scatter with the atomic mass squared, and that's coherent scattering. And so for different detectors, you have to keep that in mind. Spin independent depends on the spin of the nucleus inside your detector. Now I also wanted to mention over here, this is the astrophysics side of things. This is David's contribution. And this scales with the velocity distribution of the WIMPs, which we took to be an isothermal Maxwell-Boltzmann distribution, e to the minus v squared, where the typical velocities of these particles are around 270 kilometers per second. And so if you put all those pieces together, then you can make calculations, for example, for what these detectors would see. And based on these calculations that we did, they started building detectors. So they have to be deep underground. This, for example, is Snow Lab in Canada. And the reason that you have to go underground is to eliminate the cosmic rays that would otherwise flood your detectors. So since those early days, you now have underground laboratories worldwide that are looking for the direct detection of dark matter. And so they really are all over the world, even the South Pole. And I wanted to mention in the Gran Sasso tunnel in Italy, I wanted to say something more about the DAMA experiment, because that's the only one that has seen any hints of detection, and let me tell you what they found. So the WIMPs are moving randomly in any direction within the galaxy. So it is because the sun moves around the center of the galaxy that we are defining a reference frame, and relative to the motion of the sun, there's a wind of WIMPs that is coming at us. And so that wind, there's the wind of WIMPs. And then in addition to that, you have the Earth moving around the sun, which produces an annual modulation of the signal. So at certain times of the year, you're moving into the wind, so the relative velocity is higher. At other times, you're moving away from the wind, the relative velocity is lower. And the count rate depends on this relative velocity. So we expect a peak in the count rate in June and a minimum in December. So Dama has sodium iodide crystals in the Gran Sasso tunnel near Rome. And in fact, they do see a peak in June for, I don't know how many cycles, more than 10 years, 12 years of cycles at this point. And a minimum in exactly at the right place and the right time. I'm sorry, it's not 9, it's a 12 sigma detection. Okay, does that mean WIMPs have been discovered? I don't know. There are two problems. One is the experimentalists will not let us see their data. Makes life interesting. And also comparison to other experiments. There are many, many, many experiments that are also looking, but they have found nothing. However, it's very hard to compare. All the experiments are made of different detector materials. And so, well, I'll show you some slide of making this comparison, but first I always have to show this slide. This is one. Collier, leader of several experiments. He's at Fermilab, and then Eleanor Prelay, the leader of the Xenon experiment, Rita Bernabe, the leader of the PI of Dama. And I just love this quote on the Spaniard caught between two Italian women. And let me tell you, their discussions get very heated. So now returning to the science and this difference between the different experiments. Here I plot the WIMP mass versus the cross-section, the strength of the interaction of the WIMP on the nucleus. So as I said, Dama is made of sodium iodide, and if you were to explain what they see, then if the scattering were off of sodium, it would be here, and if it were off of iodine, it would be here. So you have possibilities around 10 GeV or around 50 GeV. However, look at all these other experiments. Well, how did I plot them on the same plot if they're made of different material? I've made the assumption that it's a spin-independent cross-section that scales as a squared, and if you divide out the a squared, you can put everything on the same plot. And in that case, it looks like if you have to be below the red curve and the green curve and so on, it looks like Dama's ruled out. Well, we don't know that because we don't know that the scattering actually scales as a squared, which makes xenon pretty powerful. So, yeah, that makes things a little tricky, and also some of these experiments are near threshold, which is also a little tricky. And I always show this for the benefit of the young people. You should think about this field because we have great meetings. Anyway, so the future of this field is that this stuff is going to happen, and what's going to happen next is, look at this, these are solar neutrinos and these are atmospheric neutrinos. We're going to start having neutrino detectors. And so then it becomes more difficult to pull out any dark matter signal out of there. You can still do it because you have a spectrum that's different between neutrinos and dark matter particles. And you can also do it with directional detection. I'll get back to that. But before I do that, I want to say that in the next 5 years, Dama will be tested. So there is an experiment. Well, first of all, the Dama data itself is going to lower energies now. And so it by itself is no longer compatible with spin-independent scattering. It doesn't work, as we showed in a recent paper. But there's still, as I said, 16 operators. We don't know. So, and all of those would work. So, however, the key is, other groups are going to use the same crystals in the southern hemisphere and elsewhere, and so in particular, I don't know why I said start cosine 100, because as of last month they actually have 60 days of data and it is working. So wait 3 to 5 years and we'll know whether or not they reproduce. They're going to be in the Gran Sasso Tunnel and also in Korea, so we'll know. All right, so we have the difficulty of comparing apples and oranges with different detector materials, and we also have, on the theory side, not only all the possible operators, but also, it turns out we don't know the nuclear physics of all these nuclei very well. Oh boy, okay? So you really have to do the experiments to see what's going on, because the theory can guide you, but it can't really tell you for sure what's going on until you have answers from an experiment. So I did mention that directional capability is the future of this field. So if you can determine which direction the WIMP came from, then you would expect 10 times as many coming along with the wind as you would in the other direction. And that is a really good way to prove that you've actually seen something, and in the end you could learn about the distribution of dark matter in the galaxy if you really get this working. So one idea that we had was to use, yes, DNA, RNA. So I've shown here, this is a nanometer thin plate of gold with one atom thick with DNA hanging down. And by the way, the reason we did this with gold is because this you can buy from the company called Illumina. They have gold with 200 bases of DNA hanging down. I forget what they do with it. It's useful for something I don't remember, but anyway, you can buy it. It's not clean enough for dark matter experiments, but they know how to attach the DNA to gold very easily. And you can do it to anything else too. Not anything, but it can be done. So what happens when the WIMP comes along? It knocks gold forward into the hanging strands of DNA and breaks them. So from these broken strands, when you built this thing, you determined this is C, G, T, da, 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 da. You know the sequence of these things. So you collect these broken strands, make many, many copies, sequence them, and by doing that, get a nanometer sensitive tracking device to find where did the gold go. Because the distance between these things is nanometers. From that, you figure out where did the WIMP come from. So you get the directionality. So that's the idea, and the irony is it's the biology side so George Church has some of this stuff sitting in his refrigerator. He's made clean DNA and so on. We need some physicists to come along and take charge now. Okay, and this is our latest thing, paleo detectors. You can also use ancient minerals that have been underground for 500 billion years, and they've been collecting WIMP tracks. So this is our latest thing that we're playing around with. And some people had similar ideas 20 years ago, but now you have nano tools to atomic force microscopes and so on, that you can identify these tracks in three-dimensional objects. Okay, so leaving the very future speculations to, well, I don't know, I mean, we can dig up these materials in deep boreholes, so we were talking to one guy, he says, what you need is blue diamonds. So I was like, okay. So then the question is, are diamonds a girl's best friend? No, black diamonds are a girl's best friend. Those of you who ski know what I'm talking about. But anyway, and you end up with thumb injuries and can't shake hands. Okay, sorry, I'm telling too many stories. All right, so on to the third way to search for these things. WIMPs don't annihilate in average places in the universe anymore, but in certain places they do. And so what happens is, where you have a lot of them, they annihilate, maybe to W's and so on, and in the end you have three annihilation products to look for: neutrinos, positrons, and gamma rays. So where would you look? Well, you might look towards the center of the galaxy, would have a lot of WIMPs, so that's a good place to look. Dwarf galaxies that are satellites of the Milky Way, that's another place. They're very dark matter rich, that's another good place to look. Or just our galaxy as a whole. So there's many ways to look for that, and there are experiments looking for all three of these end products. And so I'm going to say more about these, about looking for positrons, gamma rays, and neutrinos. All three are being searched for. And let me start with, there is a positron excess that was first seen by heat, and then by Pamela, and we looked at this a long time ago and realized, well, if you're going to have that, it needs to have a very large boost. It's not standard supersymmetry unless you do something. So either you have some kind of boosted annihilation, or you live in an overdense region of dark matter or something. And most interesting, aboard the International Space Station, led by SEMTE, is the AMS experiment, and they definitely see this positron excess. And so we have our representative in the front row of the AMS experiment, and the question is, I'm sorry, but I have to talk about this paper because some of my favorite people are the authors. Some of you know who I'm talking about. I'll hint, hint, hint. But anyway, so you can look channel by channel, such as, what if it was BB bar annihilation that created the positron excess? Well then, Fermi, which is looking at gamma rays, should have seen gamma rays from dwarf galaxies in a certain amount. If that annihilation happened to positrons, it would also happen to gamma rays. Fermi should have seen something. So mass of the WIMP, again, this time it's annihilation cross-section. So to explain AMS, you have to be here, but if you, for this BD bar annihilation, you would have to be below the blue lines because Fermi doesn't see anything from the dwarf galaxies. So channel by channel, you can rule out certain channels, but the current status is that AMS is taking more data. We have to wait and see, and in particular, some people think it might be pulsars. Is it pulsars? Is it dark matter? We don't know. So more to come from there. Okay, so the second annihilation product of interest is neutrinos. There's more than one experiment looking for that. So ice cube at the South Pole. Sweden has had a major involvement with this one, and so there are these strands of phototubes that are several kilometers below the surface of the ice at the South Pole. And they're located there, and they're looking for neutrinos. Have found some very interesting high-energy neutrino events from blazars and so on, but then nothing from dark matter yet. The other way to go is in the Mediterranean, and so we have, Valencia has a strong involvement here with Antares, which has some of the strongest bounds from the annihilation to neutrinos, and this one is upcoming. The KM3 net is this is very interesting future for these dark matter searches. The third possibility is that you look for gamma rays, and that's what the Fermi satellite is doing, and they have studied the gamma ray sky. This is what they see, the Milky Way being on this plane, and then these giant bubbles of gamma rays. And at the very center of the galaxy, let me go back a slide, at the very center there's a small spherical region that might be from dark matter. It is an excess, and is it astrophysics or is it dark matter annihilation? We don't know. There's definitely an excess sitting there. And it's consistent with dark matter, but it's also consistent with astrophysical point sources. I don't know how they're going to determine what it is. It's a really tough one. I think, so there are other bounds as well that I'm going to skip ahead and just summarize that we do have some hints here from Dama, this is supposed to say AMS. Anyway, and then from Fermi for some of these indirect detection and direct detection, and we have to wait and see what happens. So Dama in particular, that'll be tested pretty soon. So that's the one that I'm really waiting to see what happens. Well, let me mention a little bit about dark stars in the last few minutes. So this is the idea that we had. This is, well, there's a movie about it before we had our idea, but this is Doug Spolio, Paulo Gondolo, and me had this idea that the very earliest stars, before there was ever any fusion-powered stars, the very earliest ones could be powered by dark matter annihilation. Let me emphasize right away, these are stars that are made of hydrogen almost entirely. 1 part in 10 to the 3 is dark matter, but dark matter is a very potent heat source. So when the universe was 200 million years old, you would have had clouds of molecular hydrogen that began to collapse inside protogalaxies. And if they're really in the middle of the protogalaxies, there's a lot of dark matter. And so we ask the question, oh, well, what happens there? So what happens is that as this gas cloud collapses, it pulls in even more dark matter. And if these are WIMPs, they annihilate. And those annihilation products, eventually this thing gets dense enough that the annihilation product cannot escape. So then you have these annihilation products thermalizing with the star and heating it up. And yes, it's actually a star, so it's a very weird star. Then it's not very hot, so there's no fusion in the center. It's very, very weird. It's 10 AU in size. I think I don't know if I put that here, but AU is the distance between the sun and the Earth, so it's 10 times that big, even though it initially only weighs a solar mass. But then because they're so cool, they can collect more and more mass until they grow very, very large, possibly as large as 10 million times the mass of the sun and 1 billion times as bright. And if that's true, then the next generation, not the Hubble Space Telescope, but the James Webb Space Telescope, would be able to see them, and I'm really hoping that happens soon. Now, there's another interesting thing that happens, which is when the dark matter runs out inside the dark stars, they collapse to black holes. Well, at least the big ones do. And so that is interesting because there are supermassive black holes that are 10 billion times the mass of the sun at a redshift of 7, and what the heck, how do you make those? You can't start with merging small black holes. You have, if you start merging big black holes, then it might work. So that's an interesting explanation of this big black hole problem. And I don't have a lot of time to show this. Just let me show one thing, which is that this is the sensitivity of the James Webb Space Telescope, and here are the spectra that we're predicting, and you definitely can see these things in this next space telescope. Well, so there's many chances in the next decade of discovery from these different avenues. And of course, you have to have agreement between two groups in order to be convinced that you've discovered something. I don't have time to tell you about something completely different, which is there's more than, I'll just have a slide really, on sterile neutrinos. There's some hints of evidence for the existence of yet another dark matter candidate, and that is not the 3 active neutrinos, not E, mu, or tau, but an additional type of neutrino which is not experiencing the standard model interactions, but it does oscillate in and out with the ordinary neutrinos. And so it's possible that you would have a 7 keV sterile neutrino producing a 3.5 keV line in X-rays, and so that's right here. You can see this. It's seen in a number of different sources and clusters and so on. And on the other hand, this is sort of a compendium of bounds on this thing, and unfortunately this Hitomi satellite was supposed to settle this question once and for all, but it blew up and exploded. So there are upcoming experiments that are going to go test and look for this 7 keV particle. So I think I better stop pretty soon, just saying that there is some evidence for WIMPs, some evidence for sterile neutrinos, and I always like to end with a joke about dark energy, so shall I do that? Okay, so what about the 70% that we don't know? The only thing we do know is that it is causing the universe to accelerate. And my slides are, what the heck? Okay, I pushed the wrong button. That was my fault. All right, so galaxies aren't just moving apart. They're accelerating apart as observed by supernovae, and as the cosmic microwave background and clusters and many pieces of evidence that this appears to be true. What is going on here? Well, we have no idea. So the only thing it has in common with dark matter is it's also not giving off light. So dark energy is a kind of peculiar name, but anyway, so, well, what is it? So it could be a vacuum energy, and yes, vacuum energy is a real thing. Antiparticle pairs popping in and out of existence in this room, everywhere. You can measure it. It makes parallel plates attract. And if there's exactly the right abundance, that could explain the dark energy. One example would be the cosmological constant. If it has exactly the right value, it comes back. The Einstein it was thrown away as far as explaining a static universe, but it can drive an acceleration. But the natural value would be 10 to the 120 times larger than what we observed. So it was a very bizarre situation. So, and why is this dark energy just becoming important in the recent history of the universe? We call it a coincidence problem. I don't know. The theory of this thing is bizarre. It could be a decaying vacuum energy. Could be that the Einstein's equations need modification. Could be a lot of things. So on the theory side, we don't know what's going on. The only thing we're going to find out soon from observations is it constant or not? So that is something that we will get a handle on sometime soon from many different observations that are coming up. Okay, my joke. So the three of us were talking about dark matter. The three of them were talking about dark energy at the World Science Festival in New York. And there's only one thing we know, the difference between dark matter and dark energy. So there you go.
Okay, so thank you, Kadri, for this very nice talk about dark matter. So now there is time for questions. Is there any question?
I know dark matter is left over, but there is this new popular idea, the seeds, strong link in interacting massive particles. What do you think about them?
So on my list of dark matter particles, the possible candidates, it was incomplete. So there is a window left for some strong SIMPs, strongly interacting massive particles. So there is a small window left for that. Yes. It's one of the many possibilities. I don't know what more to say about it.
Okay, so any other question?
Okay, first of all, thank you very much for this nice presentation, a fresh look into the problem of dark matter and dark energy.
Well, thank you.
I have a question. As you know, there are groups advocating that dark matter can be avoided by modifying gravity. My reaction to this idea is that for problems of stationary gravity, that means for situations in which really is not the change you see in the dynamics of the problem, probably is quite easy. But there is one observation that you mentioned, which is colliding galaxies, which to me I think is a clear proof that modifying gravity probably you cannot get into a solution. And I would like to ask you, what is your reaction to that?
I completely agree with everything you said. So just to tell, in case people don't know about this, when the evidence for dark matter was only rotation curves, there was a proposal called MOND, Modified Newtonian Dynamics. Instead of dark matter, it's possible that Newton's laws needed to be modified. And the idea there would be that as you go to larger accelerations, as you get to the farther reaches of the galaxy, that Newton's laws are not quite correct. And their modification could explain the rotation curves, that is true. So originally that was just a phenomenological idea, but then variants came that were actually, you could write down a Lagrangian and make predictions and so on, and the latest version of that is Tevis. So Bekenstein was one of the people who started this, and it's tensor vector scalar theories. And nowadays, actually, some of the main bounds on this, as you said, are from the bullet cluster. But what they say there is, well, we haven't been able to calculate yet exactly what would happen in a situation like that. It's quite complicated. But it's also the cosmic microwave background that people find as irrefutable evidence for the fact that dark matter is just simply a better explanation. The Tevis people are now forced to not only introduce all these new fields into the theory, but they also have to have a bit of dark matter as well. So there are not a lot of people who are really continuing to work in this area, although some are. But it's becoming quite, it looks, and in my opinion, a lot more contrived than dark matter alone. And they even have to have dark matter as well.
Okay, thank you.
Some more questions?
Now dark energy, on the other hand, the idea of changing Einstein's equations there is very possible.
Yeah, but dark energy is only a
Something
name.
different, yeah.
It's a name. It's different.
Dark energy is a name. Yeah.
In the WIMP scenario, we focused always on this window between a GeV and maybe 10 TeV, which is probably where direct detection is more feasible, and we're getting very far in excluding
Nowadays,
dark matter
people
there.
are looking to light dark matter, going
Right.
lighter and lighter.
So can you explain what the motivation was for prejudice to this 1 GeV to 10 TeV region, and why people are abandoning it now?
So first of all, if you're going to have electroweak physics playing a role, that is kind of your natural scale, around 100 GeV. So that was the thinking, let's not go too far from that. Also, if you, at least in the supersymmetric case, if you want to have the right abundance, the relic abundance of WIMPs today to explain the dark matter, you're also driven to that scale. So if you go much lighter, then you're losing the connection. And so with this, like for example, with minimal supersymmetry. So if you're looking now at light dark matter, It's purely phenomenologically driven. It's like, well, we can build, there are brilliant new ideas for how you could go after lighter dark matter that people are pursuing. And it's because you can do it. That's why they're doing it. And so then there are theories involving hidden sectors. Entirely new. So in addition to our sector of the universe, our standard model, what if there's another dark sector that also has a lot of different particles in it, communicating with kinetic mixing, with a photon, their dark photon with our photon, and all kinds of theories that are being proposed to try to motivate this lighter stuff. If you wanted to have a WIMP, you can't go, I don't think, below 100 MeV or something like that. It's going to be hard to make it be a standard WIMP for the reasons that I said. So
The 100 MeV would still be compatible with microwave background and all these things.
yeah.
But below that, it's getting harder.
Well, no, what's harder is just getting the right abundant numbers of WIMPs today from the thermodynamics of the early universe. And if they annihilate, then how many do you have left, and so on. So that becomes harder.
Thank you.
Other questions?
But this is a very rich area at the moment on the, as far as what people are working on.
So, I have a comment and a question. The comment is about dark matter searches at colliders. So, as you said, SUSY is one of dark matter providing scenario. Also, there are generic searches looking for dark matter pairs that are produced bouncing with a jet, a photon. So there is
Sure.
a very large area, great efforts done towards this direction in Atlas and CLS experiments.
Yes.
And the question is about this 21 centimeter signal in the edge experiment. Can you comment on that?
Yeah, so there's this EDGES experiment, 21 centimeter line. So the first question is, well, 21 centimeter has a very interesting future. There's no doubt about it, that on the experimental side, that's up and coming. However, the question is, did they actually, so their systematic's limited, and people doubt that they don't really trust the data. But let's say we do. And then if you want to interpret it in terms of that you have to pull some heat out of the gas, and the way that might happen is with some dark matter interacting with it. And the dark matter has to be very peculiar. It has to have a velocity to the -4th dependence, so that it was important at that particular epoch in the universe. And people tried to write down models for this. They're kind of weird. I don't know if there are any models left on the theory side for doing that. I'm not aware of any. So it's difficult on both the experimental and the theory side, and of course you should, try anything you can. If there's something interesting here, look for it.